To understand electricity, you really have to understand what atoms are made out of. So they consist of a nucleus that has a neutral charge and positively charged particles. And around that nucleus, you have electrons, negatively charged particles that are orbiting around it. Now, if you are rubbing, for example, like when you're rubbing your hands, you are giving these electrons that are going around the nucleus of an atom energy to leave its orbit. You take him out of that structure and make them mobile. And it's really the flow of these electrons that produce electricity.
So we're looking at the role of thunderstorms and electrified clouds in the global electric circuit. So a cloud doesn't have to actually be producing lightning to be electrified. And there's what we call a Wilson current that generally runs from the top of the cloud into the ionosphere and helps feed the global electric circuit. So in the typical thunderstorm setup, it's a source of charge. In the reverse setup, or the opposite polarity, it's generally a sink. So we're hoping to find some parameters of thunderstorms, like we're looking at the speed of the updraft and how much ice is in there, and we're hoping we can relate that to how strong or weak the current is.
The ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. One very important example is how electricity and magnetism are described by 4 special equations. These are known as Maxwell's equations, and they're written in the language of divergence and curl. This top one, for example, is Gauss's law, stating that the divergence of an electric field at a given point is proportional to the charge density at that point. Unpacking the intuition for this, you might imagine positively charged regions as acting like sources of some imagined fluid, and negatively charged regions as being the sinks of that fluid. And throughout parts of space where there is no charge, the fluid would be flowing incompressibly, just like water. Of course, there's not some literal electric fluid, but it's a very useful and a very pretty way to read an equation like this. Similarly, another important equation is that the divergence of the magnetic field is 0 everywhere. And you can understand that by saying that if the field represents a fluid flow, that fluid would be incompressible, with no sources and no sinks. It acts just like water. This also has the interpretation that magnetic monopoles, something that acts just like a north or a south end of a magnet in isolation, don't exist. There's nothing analogous to positive and negative charges in an electric field. Likewise, the last 2 equations tell us that the way that one of these fields changes depends on the curl of the other field. And really, this is a purely 3-dimensional idea, and a little outside of our main focus here. But the point is that divergence and curl arise in contexts that are unrelated to flow. And side note, the back and forth from these last 2 equations is what gives rise to light waves.